Welcome to The Explainer. Today, we're jumping straight into a massive turning point in every programmer's life, making that jump from procedural programming, like C, over to the absolute powerhouse that is Java. But look, we're not just learning a new syntax today. We're talking about a total paradigm shift, object-oriented programming. So if you've ever looked at Java's seemingly endless boilerplate and felt a bit intimidated, or maybe you've wondered how these massive enterprise systems actually stay afloat without completely collapsing, well, you are in exactly the right place.
Okay, let's dive into this. Here is our roadmap for today. 1. Overcoming Java anxiety. 2. The procedural programming problem. 3. The midnight submission crisis. 4. Comparing execution models. And 5. OOP in the real world.
Section 1. Overcoming Java anxiety, a matter of perspective.
So, here's a little secret from the course instructor. Back during their BTech days, they were legitimately terrified of Java. I mean, to them, it just looked like this wall of verbose, scary-looking boilerplate. But then, they had this massive epiphany. They realized they were completely overanalyzing the structure and totally missing the substance. Once it clicked that, hey, 90% of the core logic, the loops, the arrays, conditionals, operators, all of that is practically identical to C, well, suddenly they blasted through 100 pages of a Java textbook in like 10 minutes. The big takeaway here? Don't fight the syntax. It's really just a matter of perspective. Let's actually use an X-ray technique to prove this right now. Take a look at a standard welcome program written in procedural C using your standard printf and compare it to the exact same logic in Java. And yeah, sure, the Java version looks a lot wordier right off the bat, but if you just kind of blur your eyes and look past those outer object boundaries, you'll see that familiar procedural logic hiding right underneath. It's essentially just procedural C wrapped up in clean, highly organized object boundaries. All those extra words in Java, honestly, just think of them as temporary structural scaffolding. Public class welcome? That's just the container. Make sure your file name matches it, and you're golden. Public static void main string args, or PSVM as it's famously abbreviated, is literally just the entry point method. It is functionally identical to your main function in C. And system.out.println, that's just your built-in console output. It's exactly like printf. So seriously, you do not need to stress over memorizing every single keyword on day one. Just breathe, use them as templates, and focus entirely on the logic.
Section 2. The procedural programming problem. The need for OOP.
Imagine you're building this massive enterprise student management system in procedural C, right? Say for 10,000 students. The classic approach is using parallel arrays. So one array for the names, one for roll numbers, another for GPAs. But think about this. What happens if your sorting algorithm runs to find the top performer? It rearranges those GPAs, but totally forgets to swap the student names at the exact same time. The result is absolutely catastrophic. You get silent data corruption across the entire system, there's no compiler error, the program doesn't crash, you just get totally wrong data. And this happens because in procedural programming, the data and the operations acting on that data are completely disconnected. We clearly need a better way.
Section 3. The midnight submission crisis, a real-world case study.
All right, let me set the scene for you for a high-stakes scenario. It's 11:58 p.m. on submission night. Team Alpha is sweating because they have to submit this automated trading system to Professor Sterling. Now, Sterling is notoriously tough, runs Benchmax on a highly customized secret server, and, rumor has it, sometimes borrows unencrypted student code for his private startup. Yikes. So here's their deployment nightmare. The team built this system on 3 totally different machines. Alex is on an Apple Silicon Mac using ARM64, Dev is on a Windows 11 PC using x86_64, and Ria is coding on an Ubuntu Linux laptop. They need to submit a project that runs perfectly on Sterling's completely unknown server environment, aces the benchmark, and protects their intellectual property. Let's listen in on their internal debate. First up is Alex, the die-hard C++ advocate. His strategy? Compile down to a native binary to get that absolute raw execution speed and manual pointer control. Sounds like a surefire way to crush a benchmark, right? But here is the fatal flaw. If Alex compiles that C++ binary on his ARM Mac, it is going to instantly crash with an OS error the second it hits the professor's server. C++ is strictly bound to the host hardware. To make his plan work, Alex would have to literally email his raw, easily readable source files to the professor to compile locally. That means zero intellectual property protection. Their startup idea? Stolen in seconds. Next up is Ria, the team's Python evangelist.
Her whole strategy is about development speed. With Python's pre-built libraries, they could honestly knock out the whole pipeline in 2 hours and actually get some sleep. But there's a huge catch. Plain Python files are literally just text. The professor could literally open the submission in Notepad and steal the entire trading logic before the team even leaves the lab. And even if they sent compiled Python, it's notoriously easy to decompile. Worse yet, if the server happens to be running an older version of Python than they used, boom, the whole thing crashes on startup. So they get speed, sure, but they suffer execution lag and absolutely zero code protection.
Finally, we have Dev, the Java strategist, who comes in with a winning move. Dev points out that Java compiles into a .jar file, and the beauty of this is that the jar file doesn't care if the secret server is running Linux, Mac, or Windows. As long as that server has a Java virtual machine, a JVM, it runs seamlessly. Plus, right before hitting submit, they can run an obfuscator, something like ProGuard, that scrambles all their beautifully named variables and classes into total meaningless gibberish. So the server runs the benchmark at blazing speeds, but if Professor Sterling tries to decompile it to steal the code, he just gets a wall of total nonsense. Java literally hits the sweet spot: memory safety through garbage collection, cross-platform execution, and total IP protection.
Section 4. Comparing execution models. C compilation versus Java JVM.
Let's actually walk through the technical mechanics of why this works, starting with the C execution pipeline. It is a highly direct 3-step process. You take your C source code, you run it through a compiler, like GCC, and it spits out a native binary tailored exactly for that specific machine, like an x86 processor. That binary is then directly executed by the CPU. And yes, it is incredibly fast, but the massive trade-off here is that it is strictly, fundamentally bound to that exact host OS and CPU architecture. Move that binary to a different machine, and it breaks instantly.
Now contrast that with the 4-step Java execution pipeline. You start with your Java source code, but the Java compiler doesn't make a native binary at all. It generates intermediate bytecode. And this right here is Java's absolute superpower. This bytecode is then fed into the Java virtual machine, the JVM, which is sitting on the host computer. The JVM interprets it and uses a just-in-time compiler to translate that bytecode into machine code on the fly for the CPU. This brilliant layer of abstraction is exactly what grants Java's famous write once, run anywhere capability. And this brilliantly illustrates the core technical trade-offs between the two languages. C targets native machine code, which makes it lightning fast but totally platform dependent, with manual memory management and terrible IP protection if you have to switch platforms. Java, on the other hand, targets intermediate bytecode. That makes it highly portable, it handles memory automatically through garbage collection, and offers top-tier IP protection via obfuscation. Truly understanding these architectural differences is the absolute key to making smart decisions in modern software design.
Section 5. OOP in the real world, beyond the classroom.
So we've spent a lot of time on the mechanics today, but why does all of this actually matter for your career? Well, because mastering these OOP principles is exactly what transforms a standard, run-of-the-mill coder into a highly paid, industry-ready software architect. Crucially, object-oriented programming isn't just some academic exercise, it is everywhere. From massive enterprise backend infrastructures running Java Spring Boot for global financial engines, to Android mobile development, all the way to game engines, think Unreal using C++ or Unity using C#. Even cloud DevOps tooling and mission-critical embedded systems rely heavily on these concepts. When you truly grasp how OOP pillars like encapsulation and abstraction actually manage complex systems, you are setting yourself up to build architecture in literally any of these dominant industries.
To wrap up this explainer, I want to leave you with a bit of a provocative thought to test your new understanding. Think of it as a classic exam-style scenario. What exactly happens at the bare metal hardware level when a developer tries to run a Mac M2 native binary on a Linux x86 server? And precisely how does Java's intermediate bytecode and JVM architecture completely eliminate this deployment failure? I want you to really think through those pipelines we discussed today, because if you can answer that, you have officially grasped the core paradigm shift. Thanks so much for joining me on The Explainer today. Keep questioning the architecture, and I'll catch you in the next one.